Okay, so today's chapter is all about color. Color that we see depends on the frequency of the light. So here I show light increasing in frequency from red up through yellow, green, blue, and violet being the highest frequency. If the frequency of light is lower than red, then we can't see it. It's not really light. It just looks black. And the name for that kind of electromagnetic radiation is infrared. If the frequency is higher than violet, then that's called ultraviolet radiation. And again, it looks black to our eyes. And this lambda stands for wavelength. The speed of light is generally a constant, so if the frequency increases, that means wavelength is shorter. So short wavelength would be this violet, longer wavelength would be red. And just to give you the numbers, 0.4 microns, so that's 0.4 millionths of a meter. That's about half of a thousandth of a millimeter is the wavelength of violet light. The wavelength of red light would be about 0.7 microns. Again, less than a thousandth of a millimeter. So here we have a red ball that's illuminated by white light. So what we see is the reflected white light, but since it's red, it's actually absorbing out all the colors other than red, such as green or something, and it's reflecting red. If we just shine red light down onto a red ball, it reflects red. And if we shine green light onto a red ball, well, there's no red there to reflect, so it would look black. So the color of an object depends not just on how it reflects, but also what kind of light we're shining down onto it. Here is an example of selective transmission. So this is stained glass in the Great Hall in UC. And what it's doing is it's absorbing all the colors other than blue and selectively transmitting blue light. So you can also have mixes of colors. So here's the sun, and this is what's called the solar spectrum. It's a graph of brightness versus frequency. So the sun emits some infrared, the sun emits some ultraviolet, but most of what the sun emits is visible light. That's why our eyes have evolved to be sensitive to visible light. And somehow this particular mix is what we call white light. So we have these cones, 3 different kinds of cones in the retinas of our eyes, and they correspond to being sensitive to these 3 different regions of this solar spectrum called red, green, and blue. So this leads us to the additive primary colors, red, blue, green, and they all correspond to stimulating different parts of our retina. And so if you have like this screen that you're looking at, it's a mixture of lots of little dots that are all either red, blue, or green. And when you mix those all together, they're all turned on, it looks white. If you have different mixtures of red and blue, it might look something like this purple. If you turn on the reds and the greens, you can get yellow. And in fact, by just adjusting these 3 different amounts of color, you can simulate any color that our eyes can see. So here's a golf ball illuminated by red and green and blue light. And you can see these shadows are, I guess, what are called the subtractive primary colors. So this sort of cyan is the shadow that's blocking out the red light. This magenta is the shadow that's blocking out the green light. And this yellow is the shadow that's blocking out the blue light. So if you have a mix of all the frequencies, 4.3 up to 7.5 times 10 to the 14 hertz, then that'll look like white light. If you take out all these sort of higher frequencies, then you'll just get red light. If you take out the highest and lowest frequencies, you get green light. If you take out all the lower frequencies, you get blue light. So yellow light is kind of a mix of red and green, as we said. So if you take out only the very, very highest frequencies, that's yellow. If you take out only the very lowest frequencies, that's cyan. And if you absorb out just the middle frequencies and leave the very lowest and the very highest, you get magenta. So when you look at a piece of paper, you're looking at reflected white light. And what ink does is it absorbs out certain frequencies. And so when you buy toner cartridges, you buy cyan, magenta, and yellow. And when it prints, it puts these inks on, which put the pigments down, which selectively absorb particular frequencies. So there's the magenta image, then you overlay on top of it a yellow image and a blue image, and when you combine all these, you get this color image. And it turns out, practically speaking, that it's difficult just using these inks to get a nice deep black. So we also purchase just black ink to kind of deepen the color and make it look more real. So why is the sky blue? Well, when you're looking at the blue sky, you're looking at scattered sunlight. And so when sunlight goes through the air, it encounters nitrogen and oxygen molecules, little particles that are smaller than the wavelength of the sunlight. And it can scatter that radiation. And this is called Rayleigh scattering. And this kind of scattering is more likely to happen at higher frequencies and less at lower frequencies. So this scattered light that comes into your eyes has sort of a changed color. And if you look again at that solar spectrum, the red line is the real solar spectrum, which we would call white if we were looking right at the sun. And this blue line is what tends to get scattered by our air. So as you can see, up in the sort of lower frequencies, the red, it's depressed, and so less light is scattered at red frequencies. At these violet frequencies, or blue, you'll get more scattering than you would normally from just looking right at the sun. So the whole effect of this spectrum is that it looks kind of blue. Why are sunsets red? Well, it's the same kind of thing, except what you're doing here is you're looking at what was not scattered. Light that is least scattered is light that are of lower frequencies, like red or orange or yellow. And that travels better straight through the air. So if you're looking through a lot of air, like at a sunset, this greatest path of sunlight through the atmosphere, then the sun looks kind of red. Why is water greenish blue? So if you go into the Rockies and you look at these lakes, you get this amazing, nice blue-green color. So these lakes are fed by runoff from melting glaciers, and it contains lots of silt called rock flour, which remains suspended in the water. So these tiny scatterers tend to, again, scatter the higher frequencies more so than the lower frequencies, and it gives the water this beautiful color. Okay, chapter 28 is on reflection and refraction of light. So when light bounces off a surface, we call that reflection. And what a mirror is, it's a shiny metal surface, and it contains electrons. And when light, which is an electromagnetic wave, hits the metal, it accelerates the electrons, which then re-emit light. And if you have many, or if you have two parallel mirrors, you can get many reflections from the mirror, which cause all these multiple images. The law of reflection states that if you have an incident ray of light, that will form an angle of incidence between that ray and the normal, or perpendicular to the surface, and that angle is equal to the angle of reflection between the normal and the reflected ray. So if you have an object, it's emitting rays in all these different directions, and if those rays hit the mirror, each ray obeys the law of reflection, with angle of incidence equals angle of reflection. Now if you look towards the mirror, you will see all these rays, and they appear to be coming from what's called a virtual image. It's not real, but it's a place behind the mirror, same distance behind the mirror as the object is in front of the mirror, and it has the same size as the object. Image is the same size as the object. So that image is actually reversed, and if you think of the three directions, up, down, left to right, or front to back, the image is reversed front to back relative to the object. So diffuse reflection, it happens if instead of a very, very flat polished mirror, you actually have a surface which is a little bit rough. And then when rays come down, they can scatter in all different directions. That's called diffuse reflection. And if you look around at objects in the room, almost everything you see is due to diffuse reflections. So it's important. So we talked about reflection with an L. Refraction with an R means when light is transmitted from one medium to another. And when it does that, it can bend if the speed changes. So the analogy in your textbook is if you have a wagon, these are supposed to be the wheels of a wagon, and you're looking down onto a sidewalk. So on the sidewalk, the wagon rolls quickly, but if it hits a grassy area at a diagonal, this wheel will hit first before this wheel, and so that'll tend to turn the wagon. And if you look at a normal between the sidewalk and the grass, it turns towards the normal when it's going from fast to slow. Well, the same thing happens with light. If light starts in air and goes into water, it slows down and can bend towards the normal. So here is a ray of light going from A, bending towards the normal when it goes into glass, and then bending away from the normal when it exits glass. And it turns out that by following this wiggly path, the light is actually minimizing the time it spends in the glass and getting from point A to point C as quickly as possible. So the index of refraction, N, is a number which indicates how much the speed of light differs in a material from its speed in a vacuum. Also says how much the rays bend. And the equation is N equals the speed of light in a vacuum divided by the speed of light in a material. This is a dimensionless number always greater than or equal to 1 for a material. One of the illusions caused by refraction is if you are looking at a fish and you're out here in the air and the fish is in the water, light rays will come off the fish, and since they're going from slow to fast, they bend away from the normal, making an image of the fish which is above the actual fish. So if you're standing here and you're spearfishing and you want to hit that fish, you'd better aim high. Dispersion is when white light is separated out into its different colors. So here is light refracting into a piece of triangular glass and then refracting as it exits that glass again. And this angle of refraction actually depends on the frequency of light, because light travels at different speeds if it's different frequencies inside glass. So you get a rainbow that emerges. And in fact, an actual rainbow you see out on a humid day is due to dispersion in water droplets that are suspended in the air. So if you have sunlight coming in, which is a mixture of all the different colors of light, it can get reflected and bent, and this bending angle is different for violet light, about 40 degrees, than it is for red light, about 42 degrees. And all the different colors between violet and red would get reflected at angles between 40 and 42. So if you have sunlight hitting two different droplets, well, it can bend by 42 degrees if it's red light, and that could enter your eye if it hits this top water droplet. But it only bends by 40 degrees if it's violet light, so it will only enter your eye if it hits this droplet down here. So if you have millions of droplets between here and here, you'll see all the different colors of the rainbow. And those droplets will be on the edge of a three-dimensional cone that goes between you and this water droplet region if the sun is behind you. Total internal reflection. So we said that if light is going from a slow region and emerging out into a fast region, it bends away from the normal. Well, if you keep changing the angle more and more and more, this light will bend away from the normal more and more until it actually goes right along the surface. And just beyond that is called the critical angle. And if light is incident on this surface at an angle even greater than the critical angle, then no refracted ray is possible. All the light must be reflected. And this is how optical fibers work. Light comes in and hits the inside of the fiber at an angle which is greater than the critical angle, so all of it is reflected and guided along this fiber. And so light can be taken from one end to another end, and it can carry a signal or it can carry a little color of light. Lenses. There's two main types of lenses. A converging lens, which is thicker at the center than it is at the edges, and this takes light that might be going in parallel rays and makes them converge towards a focus. And a diverging lens, which is thinner at the center than it is at the edges. This takes parallel rays of light and makes them diverge or spread out away from some point. The key features of any lens: a lens has a principal axis which goes straight through the middle and joins the center of curvature of these two sort of spherical surfaces. It has a focal point, in fact two focal points, which if you have parallel rays on one side of the lens, they will come together and pass through the focal point on the other side of the lens. And the focal length of a lens is the distance between one of the focal points and the center of the lens. So a converging lens can form what's called a real image. Here's an object and light is spreading out in all these different directions. When it hits this converging lens, all those rays can be focused inwards to form a real image on the wall. A lens defect is called an aberration, and that's a distortion. So spherical aberration is if you have a lot of parallel rays and a lens which has two spherical surfaces, all these rays will converge not exactly to a point, but to more of a region, sort of a fuzzy region. And so the fact that they don't go through a point, but instead a region, that's called an aberration. You get a fuzzy dot. Chromatic aberration is when you have light, white light, coming with all the different colors in it, and these colors are refracted at slightly different angles. So the focus for red light is out here, and the focus for blue light is here, and the actual focal region will make a little rainbow there. Lastly, astigmatism is just when these surfaces are not perfect, and depending on where the rays hit the lens, they focus in slightly different places.